In this video, we would like to make sense of the notation for the definite integral from a to b of f of x. What this symbol means is this is the signed area between the graph of y equals f of x and the x-axis. Now, you'll recall we already have a way of finding the area between a graph and the x-axis. When you have some function, say y equals f of x, and this is this area between, I should specify this, x equals a and x equals b. So I really want to focus on this area from a to b. So this is the area I want to calculate. And we already know how to calculate the area, right? The way we calculate this area is we play this game by breaking it up into rectangles and approximating the area, and then taking the limit as you get more and more and more rectangles. That's called the Riemann sum. So we already know how to calculate this signed area. This signed area just comes out to be the limit of more and more rectangles, ends going off to infinity, so more and more rectangles of the width of your rectangles. The width of your rectangles is b minus a divided by however many rectangles you have, which we're calling n. So b minus a over n times the sum from I equals 1 up through n of all these little x values. You know, like here you're at a plus 1 copy of the width, a plus 2 copies of the width, a plus 3 copies of the width, and so forth up until you get to the end. And so we'll just call that, let me just call this value x1, x2, x3, all the way up to the last one, xn. So we'll just call this f of xi, where that value would just be given by a plus I copies of the width, right? So that's what this value is. These are sometimes referred to as sample points. Okay, so that is how you calculate this area. But how do you get from this formula to this new notation I'm introducing? Why would we use this as the notation for the area under the graph? Well, the idea of this notation is as you take more and more and more rectangles, as n gets bigger and bigger, these rectangles will get smaller and smaller and smaller. And so as the width keeps getting smaller and smaller, the width of these rectangles each keeps getting smaller and smaller, I'm just going to call that width something. Maybe, something it's called like delta x. That's just your size of the width. As the limit goes off to infinity, it gets smaller and smaller and smaller till it's infinitely thin. You don't actually get there, but in the limit, you're approaching infinitely thin for your rectangle. And so in the limit, this goes to dx, which just represents an infinitesimally small width. So this is an infinitely thin width. So this limit, well, you could rearrange this to just put this width on the other side. This is multiplication, so you could put it on the other side if you want to. And then this is just asking what is the limit as n goes to infinity of adding up more and more and more rectangles. So you're adding up more and more and more of these guys times that infinitesimally small width. This is headed towards dx. This width is getting smaller and smaller, headed towards dx. And what do you end up going from then? Well, then you end up with, you're summing f of x values. You're summing, so instead of sigma, I'll do a long s for summing f of x values. This is what you should be thinking. This is f of x values, where those x values start here at a. As your width gets smaller and smaller, you're starting at a, and you're moving towards b of f of your x values times an infinitesimally small width. So height times infinitesimally small width. So that's how this notation is a shorthand. It's an abbreviation for our typical our typical formula for Riemann sum. So this is me trying to write in a concise way the Riemann sum formula. But whenever you see this, you should just think it's the area from A to B between the graph of y equals f of x, between that graph and the x-axis, That width has become infinitesimally small. That's what the dx stands for your rectangles. Okay, so adding up infinitely thin rectangles to get your area. That's what the notation means. Now there's one word in here that should stand out to you, and that's the word signed. What do I mean by signed? By signed, I just mean positive or negative. Now, in most of the examples we're seeing, in this example, the area is positive. It's positive area because it's above the x-axis. But if you had a function that dipped below the x-axis, something like this, then while this area over here would be positive area, this is positive area, all of this area in here is positive area, when you calculated any area between the graph and the x-axis, I say any area over here, you would come up with a negative answer. The reason it would be negative is because when you calculate f of these values, they're negative numbers. So this portion of the area would be negative, that portion of the area would be positive. If your A and your B is from here at the beginning, maybe this is your A, all the way to B, you calculate the area. What you would actually be calculating is this much positive area minus that much negative area. And we'll see some examples of that so you can see what that looks like. Okay, well hopefully that helps you understand what this symbol means. Just the area, positive if it's below, negative if it's below, positive if it's above, negative if it's below, between your graph and the x-axis. Once we have this notation, we can just note a few properties of it. So here are some properties of the definite integral. This is called the definite integral. So what are the properties? One property is if I ever ask you, what is the area from A to A? Like maybe your A is just 1. From x equals 1 to 1 of whatever function you want, dx. That function, its area from A to A, that's like I'm just asking you, what is the area of just this one slice right here? You know, not the whole thing, not from A to B, but from A to itself, just area of one slice. Well, that's an infinitely thin slice. It has no width, right? That's just one slice, so that area will be 0. Hopefully that makes sense. What if I want to find the area from A to B under some graph and add to it the area from B to C under some graph? So here I did it from A to B. What if we extend this a little bit? You know, maybe this guy continues on, and over here is some C. You know, here's C. And so this first part is giving me this area here from A to B. And then the second part is giving me this area from B to C. You calculate whatever that area is. What does that come out to be? Well, it would end up being just your total area from A all the way past B to C. From A all the way to C of f of x dx. Now that's assuming this is a nice function you can actually calculate what the area is. If the function is not continuous, if there's an asymptote or something, maybe this area is not well defined, maybe it goes off to infinity. But assuming it's a nice continuous function, then you have this property, the area from A to B plus the area from B to C is just the area from A to C. Now these two properties we can put together. We can put these together to say, well, what would be the area from A to B plus the area from B to A? Now this might seem kind of strange. Like I know the area from A to B, that's from A to B, but this seems to be written backwards. Usually we do the guy on the left first, and then the guy on the right. Here we flipped it. Now I've gone from B to A. Now I'm saying then do the area backwards. That seems a little confusing. Let's try and make sense of this. By using the property above, this should just be the area from A to B back to A. That's just the area from A to A. From A to B and B to C is A to C. So A to B and then B to A will just take you back to just A to A. But we just said that is 0. Which means now if we solve for this guy, the area from B to A of f of x comes out to be, well, in order to cancel with this first term to give me 0, it must be the negative of the area from A to B. Okay, so you can just think of this as a formal convention. Typically, you write the area from the left to the right value, the area from like 1 to 3. But if I instead wrote the area from 3 to 1, I would just figure out what is the area from 1 to 3 and then make the result negative. So whenever these guys on the top and bottom are the opposite of what you expect, you can just flip it around and then make the answer negative. Okay, those are a few properties of the definite integral. To wrap up, let me give you a couple more properties of the definite integral. How would I calculate the definite integral from A to B of f of x plus g of x? Okay, so what do I have in mind here? I guess I need another picture for this. So here I have some picture in view, some picture f of x, which I don't know, maybe some picture like this. So here's my function f of x, y equals f of x. And then I have some other function in view, g of x. And maybe it's some function like this. This is my function g of x. And I can calculate the area from A to B. From A to B, I can calculate that area under f of x. I can calculate area under g of x. But what would be the area under f of x plus g of x? Well, here we're going to need one more function now. I need to try and draw a graph of the f of x function plus g of x, f of x plus g of x. And here the y values will just be the y values of the f of x function plus the y values of the g of x. So he is just going to be, this function is just going to have this much added to it. So he's going to start up here, and then on this side he'll have this much added to it. So he'll end up down here. So that's going to look something like this. Here's the f of x, here's g of x, here's f of x plus g of x. This is the graph y equals f of x plus g of x. And so now what I want to do is think, what is the area under f of x plus g of x? But if I go to find that area by breaking it up into rectangles like I've been playing this little game, I want to break this up into little rectangles. The key realization is the height of each of these rectangles is just the height of the corresponding rectangle in the g of x graph plus the height of that rectangle in the f of x graph. Which means when I sum up all the areas of all those rectangles, it'll be the same as just summing up all the f of x rectangles plus all the g of x rectangles. And so this will just come out to be the area under f of x plus the area under g of x. Okay, so that was a mouthful, but what I'm saying is just that the area from A to B under the graph of f of x plus g of x, under this whole graph f of x plus g of x, is just going to be the area under the g of x graph plus the area under the f of x graph, because the height of this is exactly the height of those two added together, right? So there's our property. There's a very similar property that if instead of doing f of x plus g of x, if we did f of x minus g of x, it would come out to be the same thing. So you can do plus or minus, it comes out to be the same thing. What if you want to multiply? What if I want to find something like, what is the area under, I don't know, 2 times f of x dx from A to B? Well, one way you can think about that is that would just be the same thing as the area from A to B of f of x plus f of x. And then we use the property above, that's just the area under f of x plus the area under f of x. So that just comes out to be 2 times the area from A to B under f of x. And there's nothing special about 2. If I had done 3 or 4, any other constant as well, I would have the area from a to b of some constant times f of x. It's just that constant times the area from a to b of f of x dx. Another way to see this is think when you multiply a function by a constant, you're just scaling the height. If you times it by 2, you're making that function twice as tall, which makes the corresponding area twice as large. When you double the height of something, you double its area. When you triple the height, you triple the area. Or k could be a fraction. When you cut the height in half, the area gets cut in half. So here are a couple more properties of the definite integral.